Imagine that you want to rob a bank. Now, don't worry, this isn't some crazy ethical dilemma that I'm asking you to consider, but that being said, you do belong to a gang. Right, so gang-affiliated you wants to rob this bank. Inside of this bank are some number of vaults. Just for simplicity, let's just say that there are 2 vaults. And inside of each of these vaults are 4 golden bars. Now, this seems pretty simple. You tunnel into the vault, you take the bars, you go back down out through the tunnel, and you're in Mexico by daybreak. But not quite. You see, the intel that you've recovered says that there's a major flaw. One of these vaults, the gold bars, are entirely fake. And in the other vault, only half of the bars are real. Now, disregarding the fact that this is a terribly inefficient way for any bank to handle any amount of currency and still make a profit, that's the situation that you're left with. Now, moreover, your gang leader has made it very clear that anybody who takes up any space in the getaway car without real gold slung over their shoulder will be immediately executed. Now, the tunnel that you built into the vault is too small to bring any lab equipment through, and to be honest, you don't have enough time to verify which of the gold bars in this vault, if any, are real. However, you do have one tool at your disposal. In front of each of these gold bars are 2 tokens, and the combination of either white or black indicates the location of that bar. So in front of one, you have 2 black tokens. In front of another, you have 2 white tokens, and then you have a white and a black, or a black and a white. Now, in the corner of the vault is the tool that can help you. We're going to call it the Goldatron 3000. Now, the Goldatron has 3 slots on the top and 3 slots on the bottom. In the first 2 slots, you place the combination of tokens for the bar that you want to test. So say I want to test the second bar, I take a white token and place it in here, and a black token and place it in here. In the third slot, you place a black token all the time. If you are in a vault that has real bars, the Goldatron will change this black token to a white token at the bottom only if the first 2 tokens represent the location of a real gold bar. If you're in a vault that has no real gold bars, then no matter which of these combinations you place into the first 2 slots, the black token will always come out as a black token. Now, unfortunately, the Goldatron takes 1 hour to complete, which just so happens to be the maximum amount of time that you're willing to spend in this vault before the bank sounds the silent alarm and the police come and get you. So we do have a way of testing, unequivocally, whether or not any of these gold bars are real. Unfortunately, we only have time to test one of the gold bars before we have to leave the vault. In this example, the Goldatron is what we call a classical computer. A classical computer works off the same basic principle as the device that you're watching this off of, because your device is a classical computer. In any of these classical computers, information is stored as either a 1 or a 0, or as off or on, or, as in this case, black or white. As a result of this binary system, the Goldatron can only test one of these bars at a time. You might think of this as analogous to when your computer would try to guess a password. It would have to guess each individual password one at a time. Alright, so back to the vault. You seem at a loss. However, you do have one trick up your sleeve. You have in your pocket 6 of these so-called peat boxes. They're named peat boxes by Terry Rudolph, who's the quantum physicist who came up with this thought experiment. Now, peat boxes only have one goal in life, and that's to superpose our tokens. And I'll explain what superpose means in just a moment. Inside of each of these peat boxes is a coin. When the coin is flipped, if it lands on heads, let's say, the token will fall through without any incident. However, if the coin lands on tails, the token, if it's black, will be switched to white, and if it's white, will be switched to black. Now, we place each of these peat boxes on each of the slots on the top and on the bottom. We do the same thing that we did before. we take 2 tokens for one of the bars, place them in the first 2 slots, and then place a black token above the 3rd slot. Now, we place these P boxes and we make sure that we aren't able to observe the tokens anywhere between dropping them into the first P boxes and when they come out of the entire contraption at the end. Now, an interesting thing happens. When we do this, we can take any of those bars and drop any of those combinations through, and when we do that, at the end, we will have tested every single combination of bars in that vault. So how does this happen? At the moment that any one of our tokens left a P box, it had an equal probability of being both white and black. So because we're not able to observe the token from here to here, quantum physics says it actually is both white and black. Now, this is where the token analogy kind of stops making sense, but I've found it only stops making sense because the physics behind it becomes equally unintuitive. Every elementary particle in the universe has certain properties about it, such as spin. Every electron has spin. When we observe an electron, we know that it either spins up or it spins down. However, when it's not being observed, quantum physics says that it has an equal probability of spinning up or down or in any infinite number of other directions. As such, the electron is both spinning up and down. This is called a superposition. The same thing happened to our token in our analogy. When it went through the P box, it had an equal probability of being both white and black. So, quantum physics says, because we don't observe it, it is both white and black at the same time. Now, every elementary particle also has what's called a wave function. Now, a wave function is kind of a visualization of the superposition of that particle. So in this case, we have a white token and a black token, which can be thought of as particles, and they have these wave functions. Now, after the black token and the white token go through these 2 P boxes at the front, as well as the black token through the 3rd, their wave functions begin to interact. Just like if you go to the beach and you see 2 waves collide, with one wave going forward and the next wave coming behind it, the resultant wave is much bigger. So when these tokens, their waves, interact with each other, the resultant wave is actually all of the possible combinations of those 3 tokens. So that means that the Goldotron 3000 is actually testing every single combination of those 3 tokens. What happens as this misty cloud state, these waves, travel through the Goldotron 3000 is they're going to eventually, in an hour, reach the second set of P boxes. When they reach the second set of P boxes, the same thing that happened at the first set of P boxes is going to happen. The waves of the different superpositions are going to interact, but now they're the superpositions of superpositions. So they're going to become very big and very complex. But these very big and very complex waves are actually going to start to cancel each other out. And by the end, you're going to be left with only one answer. Now, if the Goldotron 3000 is placed in a room where there are real bars, one of the combinations that went through the Goldotron will have been one of the 2 possible real bars. And then the Goldotron will have changed something somewhere, and we don't know where, and we don't really need to know where. If the Goldotron is placed in a room that has no real gold bars, though, if you were unlucky enough to dig up into that vault that had no real gold bars, then nothing will have changed. At the end, when all of this stuff is canceled out, we will be left with one possibility of tokens, which will fall through these P boxes. If anything in these tokens at the bottom have changed from the top, we know that 2 of the 4 bars in our vault are real, and we can just take all of them. But if nothing has changed between the bottom and the top, we know that we are in the vault with only fake gold bars. Now, this is what a quantum computer does. It doesn't compute anything faster. It still took us 1 hour to test one set of tokens. But as a result of this superposition, we've tested every single combination of tokens. So the time of computation doesn't get any faster, but the amount of computations that the computer needs to complete decreases immensely. So what are some of the applications of this? Well, a quantum computer right now, one of the things that they're looking into is what I mentioned earlier. It's password encryption, it's password protection, it's security, it's cybersecurity. Now, if you were to guess that password with a classical computer, like I mentioned earlier, it would have to test every single possible password and input it one at a time. However, with a quantum computer, you can give it a certain set of parameters, and then when you find a way to superpose these bits and make them quantum bits, you can test every single password in one go, or at least in less number of computations than you would with the classical computer. As a result, the time that it takes to guess the password is greatly reduced. I hope you enjoyed that video. There's lots of math and other stuff that I didn't write up here because it just gets a little bit too confusing. But I hope that you understand now that quantum computers are extremely powerful computing tools for certain situations where lots of different variables or combinations exist. They don't act as a replacement for classical computers, but they do have very, very important scientific and security applications. If you'd like to learn more, definitely, there's tons of videos out here on YouTube, and there's tons of stuff online. I highly suggest you read some excerpts or the whole book, Q is for Quantum by Terry Rudolph, and that's where this thought experiment came from, and have a good day.